Hi everyone, and welcome to the 101 Earth Observation Virtual Lecture Series. This series is delivered by the Satellite Applications Catapult in partnership with Wild Labs. My name is Cristian, and I will guide you through a journey through Earth observation. So this series of lecture is composed of different parts. The first part it's all about how remote sensing or Earth observation work, and this is also called the physical framework. This series is composed of different videos, different short videos, and we see here how those videos are actually named. We will see, for example, a first introduction of remote sensing, followed by a more theoretical view of electromagnetic radiation principle, and finally, we will have a look at basic properties of Earth observation imagery. The second part of our series is about what remote sensing can do. So we will see several application examples. We will have three different videos. So first, an overview of applications. Then we will go much more in detail into passive remote sensing and active remote sensing. The third part of our series is about how remote sensing is being used. We will see specifically two case studies. We will see an environmental remote sensing case study about the search for lithium in the UK, in a region called Cornwall, and the conservation remote sensing study about wildlife corridors. Finally, the last part of our series is how do I actually get started? So once we get all this information about remote sensing and Earth observation, where do I get data? Where do I process data? We will see this in 5 different short videos, which will cover public mission and data. We will see specifically Sentinel and Landsat missions, and then we will also have a look of Earth observation derived products which are publicly available, followed by data access and processing, and finally we will have a look at the commercial world. Hello, and welcome to the 101 Earth Observation Virtual Lecture Series, delivered by the Satellite Applications Catapult in partnership with Wild Labs. This lecture is about the remote sensing process. Let's start with the basic definition. So what is remote sensing? Remote sensing is a technology that measures electromagnetic radiation to extract information on this Earth land surface, sea, and atmosphere. This sentence that describes remote sensing captures exactly the essence of it. So first of all, we are talking of a technology. So something that is a technological, let's say, we are in the technological sphere. And what is important, we measure, so it's a technology that measures electromagnetic radiation. So we are measuring something to do what? To extract information. So at the end of the day, what we want to have is information on what's happening on Earth, on surface, sea, and also the atmosphere. That's why we call it Earth observation. Remote sensing is a more general term, and Earth observation is part of remote sensing. A bit of a history of remote sensing. So remote sensing started really long time ago, in early 1900, with pigeons. So if I remember well, in the US, pigeons were used to monitor cities and to capture the urban landscape with cameras attached to them. From pigeons, we moved to satellite constellation nowadays, and there are so many micro satellite constellation up there. So there is a clear technological evolution. Let's have a look at advantages and limitations of remote sensing. Remote sensing, by definition, is unobtrusive. So we do not touch the surface. So we sense remotely. This is a clear advantage because we do not need to be specifically there. Another big advantage is that we can systematically collect data. So we can have a possible systematic data collection. So that means that we can capture data when we want, at the time that we want. By this way, we can provide meaningful information of whatever we are targeting. Which are the limitations? Remote sensing might be oversold. So that means that we are not actually able to provide all possible information about the Earth. So we can think, for example, to something that happens very deep in the surface that is generally not feasible to capture. Another limitation are human errors in interpretation and processing. So remote sensing needs quite some skills and expertise when it comes to interpreting our images and process our images. We will see more clearly in the next videos. And finally, remote sensing can be expensive. Although there are like sources of data that are publicly available, there are other sources of data that are not. Again, we will see this better in part 4 of our lecture, but remote sensing can also be expensive. Remote sensing has a process defined, so which is called the remote sensing process, and this is the core of our lecture. You see this picture taken from a book. You see the reference there, Introduction to Digital Image Processing from Jensen. This is a book that I'm using in my lectures, and you will see several figures from this book through this series. So let's have a look specifically at the remote sensing process. We start with the statement of the problem, so which is what we want to do. So for example, let's say that we want to map rice fields, and we just want to have like a mapping of rice fields. That's our problem. To do that, we need to collect data. Data can be of different types, as you see here, not only remote sensing data, and we will see better in the next videos, but also potentially in situ measurements. We might have a problem that requires some calibration of models and therefore requiring some data collected on ground. So this is the second part of the remote sensing process. The third part of the remote sensing process is the data to information conversion. In this part, we actually do the processing of the data. So we get our images and we derive the relevant information. In our case, they were like simply rice field, maps or boundaries. So this is our third part of the process, and it involves really like what is called digital image processing. Final part, it's the information presentation. Once we got our product, we need to present it to stakeholders or to researchers, to whoever is this study for. And within this part, we often also carry an accuracy assessment of our results, alongside a proper presentation of the results. So those 4 parts of the remote sensing process are very common, and we will see this through all this series. Let's enter a bit more in detail in each of those parts. Statement of the problem. I mentioned rice, but as you see here, there are really a large variety of potential Earth observation applications, from Earth system and environmental science to global change research, climate change, meteorology. It's a very important aspect of remote sensing, sustainable development, safety and security, mobility, traffic, resource management, forest agriculture, and civil engineering and planning. So those are all part of potential Earth observation application. Once we got our problem, we need to collect data. Remote sensing has specific type of data that can be collected and can be categorized in mainly 2 categories. You see 3 here, but the main categories are let's say 2. So what we call optical remote sensing, where the sun is the main source of energy, and active remote sensing, where the sensor itself is actually transmitting energy and receiving energy. The energy that is like reflected on the surface is the information that we want. We will go more in detail into the description of those specific sensors in the next videos. Good, we got our data. So what do we need to do now? We need to convert this data into information. Information is the key part of remote sensing. At the end of the day, what we have is an image, but we work on computers, so on digital images. And what the computer gets are just a bunch of numbers. So what we need to do is to process these numbers to get information. How do we do that? A colleague of mine properly defined this in different steps. The first step is the image acquisition and correction. So where we get our image, so this bunch of number, and we potentially correct. You see an example over there where we have like an image over a bay in California, which is very dark. So a first step could be simply to transform this image into something that is brighter. And this is through several filtering, which are also called low-level analysis. Once we got a better representation of our image, a sort of image enhancement, we can do the mid-level analysis, where we start extracting information out of it. So, for example, in this case, we want to create a land cover map, where from this image we get different portions of the land represented properly and classified properly. So what we are doing is that we extract information and we cluster and segment information, so that we have the image that we see at the right, which is a colorful image, but which doesn't have actually the land cover represented. This is coming at the last part of the analysis, which is the high-level analysis, where we actually classify this sort of information in different classes. So these steps 1, 2, 3, and 4, it's quite common in remote sensing, and this is what it's called what is called data to information conversion. Finally, we need to present this information. And this information can be represented in many ways. It's always important to present this information in a proper way, potentially in a catchy way, if you want to attract stakeholders or having like a proper representation of our results. You see an example in this slide where we have it's a different subject in this case. What we see here it's a bridge. And the points over there, they're simply measurements of the displacement on the bridge. We will see this specifically in the synthetic aperture radar lecture, but what I want to focus here is how we present this information. So our information is simply the measurements, but how do we present it? We present it in a 3D way with several layers of information. We create a platform around it, and we do this like in a sort of like fancy, catchy way. So I want to stress that it's very important to present the information properly. So we have seen these 4 different steps of the remote sensing process. Hello and welcome to the 101 Earth Observation Virtual Lecture Series. This series is delivered by the Satellite Applications Catapult in partnership with WILDLABS. This lecture is about electromagnetic radiation principle. What remote sensing is measuring? Remote sensing is measuring what is called electromagnetic spectrum. And this is a concept that is fundamental in remote sensing and Earth observation. So we see this in this figure. So we've got the sun. The sun is transmitting energy in form of light. And light, it's composed by photons, which are also known as light quanta or energy quanta. Those photons, they have a particular physical property, which is called wavelength. So mainly photons, they travel in vacuum in this form. So this is a sinusoidal form. And the wavelength is the distance between 2 peaks. We are talking of very little, clearly, distance and measurements, so you see nanometer. But depending on this physical measurement, we can classify the light in different categories. And we see these different categories in the right part of the figure. Those are also called bands. The human eye can see only a limited portion of it, which is what it's in color there, from the violet limit to the red limit. And the bands, they have different names. So we have a blue band, a green band, a red band, and so on. There is a lot outside, actually, the visible part of the spectrum. So we've got, for example, ultraviolet, the ultraviolet part for small wavelength, or for larger wavelength, we've got like the near infrared, far infrared, also short wave, infrared, and so on. So as you see, the electromagnetic spectrum has a large part and is large and has different bands. Remote sensing sensors can capture this in almost its entirety at different bands. Why this is important? This is very important because, as we see, some of the measurements that we can capture with our sensor are very relevant in portion of the spectrum where we actually, do not see what's in there. So, for example, in the infrared portion of the spectrum, we will have some applications that are actually driven and triggered only in that part of the spectrum. However, this is the most important concept of remote sensing, electromagnetic spectrum. And it's important to understand that there are different parts of the spectrum that relates to different wavelength of photons. Actually, what is important as well is the atmosphere. So most of our sensors, they fly in space. So at a certain altitude, can be 500 kilometers, can be even more than that. There are different portions of the orbits, which are called differently depending on where satellites are. But what is important is that being so far, the measurements that we have, they pass through atmospheric layers. No? So we have our Earth, where we want to measure any information, and we have our sensors. Between those, there is the atmosphere. The atmosphere has a big impact in the electromagnetic spectrum, as we see in the figure in this picture. Specifically, the energy that is reflected, it's different at the top of the atmosphere or at the bottom of the atmosphere. Generally speaking, we want to measure the bottom of the atmosphere, so we want to measure something at the Earth. And we see how the radiation, it's what we see there in yellow. There is a general decay due to some properties, but it's important to see that there are actually some windows there where we don't have any information. And those windows there, they relate to different atmospheric components. So what is important here? What's important is that remote sensing system must function within this window. So when we are building a remote sensing sensor, we obviously need to build a sensor that captures this energy, this electromagnetic spectrum properly, and doesn't function, for example, exactly only maybe in that window where we want to have information. Now again, what we are measuring. So we have in optical Earth observation the sun as main source of energy, and we have our sensor. Sun is transmitting light, which is reflected and bounce back to our sensor. The reflection and the information that comes to the sensor is directly related to what we see on ground. Let's have a look at this picture. So in this picture, we have like our electromagnetic spectrum in the x-axis with all the wavelengths. So as we explained at the beginning of the spectrum, it's the visible part of it, so what we can see. But everything that is like after around 700 in this plot is not visible. In this case, it's the infrared part of the spectrum. What is important here is that, as you see, different components on ground behave differently in terms of spectral energy that is like received at our sensor. So let's have a look at few examples here. Water. Water is this blue line at the end. So as we can see, the quantity of information that comes to our sensor is really, really low through all the electromagnetic spectrum. So we are very low here with just a little information on the visible part. Other components, they behave differently. So we can see this as a sort of a fingerprint. So every different component, grass, concrete, red brick, sand, and so on, has its own unique fingerprint into the electromagnetic spectrum. And by capturing this properly, we can actually classify those components. And we can have information about those. An important point here is the difference between radiance and reflectance. What we measure at the sensor is the radiance. So this is the variable that it's directly measured. Again, it's how much light the instrument sees from the object being observed. This actually includes all the atmosphere and also topographical impacts. What we want to know is actually what is really happening on the surface. So we need actually to remove these additional components through some operations, which are called radiometric correction, that transform the radiance into what is called reflectance, which is the direct ratio of light leaving a target. So basically it's the property of the material being observed. Some interesting facts here. If you recall, the beginning of the spectrum reflects to the blue, green, and red colors. Actually, if by looking at how those spectral signatures are, we can understand why we see the surrounding with those colors. So let's have some examples. So let's see some examples. So let's have a look at the concrete, which is like the highest figure up there. So as you see, it's kind of flat, or it moves slightly, into the visible part of the spectrum. So that means that there is a balance. There is an equal balance, more or less, between the colors. That's why concrete appears gray in our eyes. If you look at the red brick, which is the next curve, we see how the weighting of the blue and the green is much lower than the red, which is very high. So we have like this sort of uptrend. That's why the brick is red. So that's why we see it red. So we can actually explain what we see, in our environment just by looking and just by studying the electromagnetic spectrum. What about the other technology? The other technology is called synthetic aperture radar. So this is a completely different technology because we don't have anymore the sun, which is transmitting the energy, and our sensor, which is receiving the energy that is transmitted by the sun and reflected back. In this case, the sensor itself is transmitting a signal, which is bounced on the surface and is like received back, like a bat, in this example. Now, SAR, it's a different system, clearly because of that. The good point of SAR is that it's actually weather independent. So while optical remote sensing can actually see the clouds, because we have our source of energy, again, which is the light, the sun, the light, pass through the atmosphere, and then we see what is coming back. So if you have clouds, we basically see the clouds. SAR works at the different part of the spectrum, works at microwaves that actually are able to penetrate the clouds, and we are able to get cloud-free imagery. We will see more about SAR in the next videos. So as I just explained, SAR operates in the microwave domain. If you look again at the electromagnetic spectrum, and we look at the plot just next to the sun picture, we are in the lower part of it. The name of the bands, in this case, they're slightly different. So we don't have anymore a classification depending on the colors, blue, green, red, ultraviolet, infrared, and so on. SAR has a different terminology that depends, obviously, again on the wavelength, so electromagnetic spectrum. The name is its own letter. So and you see in this table here the different naming. The most used bands in synthetic aperture radar are the X band, C band, and L band. They operate at different frequencies, and while X band has a shorter wavelength, L band has a slightly larger wavelength. So we are talking in this case of a centimeter of wavelengths, so which is obviously much larger than what we described before for optical data. The main information coming out from SAR remote sensing, it's called backscatter. So this is different from the radiance and the reflectance that we described before, and it comes from this concept of energy transmission and reception. So a single radar image is usually displayed in this way, like in a gray scale. And the intensity of each pixel here represents the proportion of the microwave backscatter from the area of the ground. So again, we have our system which is transmitting energy. It bounced, in this case it's an island, we see an island, and is reflected back. We see this in black and white because we have only, let's say, a one-dimensional signal. To be actually precise, the signal is composed in what we call amplitude and phase. We will see this better in the next lecture, and in this case we are focusing only on the amplitude. But this is the main information that we typically see with SAR data. Our backscatter depends on many different components and factors of what's on the ground. It depends much more on the geometry rather than maybe on the physical properties of the ground, as we have seen with optical data. So it depends on the type, on the shape, on the orientation, and so on. There is a big dependency on SAR also on the moisture content of the target area, as well as system considerations such as the incidence angle for which the wave is transmitted, so if it's transmitted with an angle, with a different angle, and so on. The main information here is called backscattering coefficient, and it's usually measured in decibel. It's also called normalized radar cross-section. We will see in the next videos several applications that use that specific data. Hello, and welcome to the 101 Earth Observation Virtual Lecture Series. This series is delivered by the Satellite Applications Catapult in partnership with WILDLABS. This lecture is about basic properties of Earth observation imagery. We have seen in previous lectures the main concept of remote sensing, which is the electromagnetic spectrum. Within this video, we will see several resolution components that link to the main concept. Let's start with the first resolution, which is the spectral resolution. So we have seen how the electromagnetic spectrum can be categorized in different bands. Our remote sensing sensors, they capture a limited number of bands, and the number and the dimension of those bands or wavelength intervals is the spectral resolution. So let's have a look at this figure here, and we see the second part of the figure. We see that we have four different bands: the blue, the green, the red, and the near infrared. So that means that our remote sensing sensor is capturing those four different bands, which are also shown as black and white figures in the stack below. Now, by combining those bands, we can create colored figure. So for example, by combining the blue, the green, and the red band, we create what is called natural color composite figure, as we see over there. This sort of images, this sort of pictures are what we usually see with our eyes. So this is a natural color representation. And this imagery is what we see on a day-by-day basis, for example, by looking at apps in our phone, such as Google Maps, Apple Maps. So this is the type of images that we see. We can create as many color composites that we want, but I just want to showcase another very popular color composite, which is called the false color composite, which is combining the green, red, and near infrared bands. In this case, the color are not as we see, because we see, for example, that the vegetation appears as red. This is actually quite a good color composite to study vegetation, phenomena. Another resolution is the spatial resolution. The spatial resolution is the smallest angular or linear separation between objects that can be resolved. We can see an example in this figure, so where we have different resolution of an image over an arbor in the United States. So we see that, for example, just looking at the bottom, we have a resolution of 80 by 80 meters, then we move to 40 by 40, and so on. If you look at the 80 by 80, we can say that that's an arbor, as well as the 40 by 40 or 20 by 20. We start having some more information from the 10 by 10, and this information actually increase by decreasing those separation. So for example, in the half meter by half meter, we see so many details. Now, why this is important? Because in order to detect, the feature, we need to understand what is the spatial resolution of our images. The spatial resolution is generally linked to the to data distribution policies. So specifically, we have like open access data that is typically up to 10 meters. So we are like in the middle of this figure. While higher resolution, they are generally part of commercial data. So this is also called very high resolution remote sensing, for example, the half meter by half meter. Anyhow, this is important to classify remote sensing sensors, not only spectral resolution, the number of bands, but also spatial resolution, how fine we can see details in the image. Now, we do not always need all the bands. It actually depends on the application. So we see this example from what we see here is actually from a sensor, a commercial sensor called WorldView. So again, we see all the bands in the spectrum, the visible part in the middle, the non-visible, which is the rest, near infrared and shortwave infrared. We see how the application here, they can be triggered by different bands. So let's focus on some of those. So for example, if you want to study soil and vegetation, we typically need that portion of the spectrum, so around the visible and the near infrared part. But if we want to explore more geological application, more oil and gas, we need to go further down, so in the shortwave infrared. So we see how actually, we do not always need all the bands. It really depends on the application. So this is the concept of this slide. It's very nice to have all the bands because, as I have showcased at the beginning, we can actually fingerprint the contents that we have on Earth by studying that specific trends. Now, sensors that they have like a large number of bands, up hundreds, they're called hyperspectral sensors. While sensors that they capture only one band, they're called panchromatic sensors. In the middle, usually 10, 15, 20 bands, so those sensors, they're called multispectral. There is a trade-off here between spectral and spatial resolution. Unfortunately, we cannot capture a lot of bands, so we are in the hyperspectral domain with a very fine resolution, centimeter. So there is a trade-off here. So as you see, we have a decrease in the resolution depending on the spectral resolution. But what is important here and what I want to stress is the terminology. So for the first time, we mention and we see hyperspectral. So hyperspectral are sensors that they capture, again, lots of bands. And while multispectral, a limited number of it, 4, 15, 20. Final resolution is the temporal resolution. Temporal resolution means how often and when the sensor records imagery over a particular area. I mentioned in the first video how remote sensing can provide with a systematic collection of data. Systematic collection of data means data captured at that specific times. Some sensors, they capture data in a regular way. So that means that data is captured at specific times. And the distance between the time, it's called temporal resolution. For satellite remote sensing, this is often linked to what is called repeat pass, which is when the sensor can acquire over that particular area with exact geometrical configuration. So this is the temporal resolution. If we talk about SAR, SAR is again a slightly different sensor. So we need to introduce here now the geometry of SAR. SAR has a side-looking geometry. That means that the signal is transmitted on a side. So it's not transmitted vertically, but on a side, as we see over there. The direction of the transmission is called slant range. The direction of flight is actually called differently and is called azimuth. What we capture on ground is called swath. Now, this is quite important to understand, especially this terminology, because it's very common in SAR images. So SAR are acquired in these two different directions, azimuth and range. So when we see an image, like in this case, in this specific case, the y-axis is the range and the x-axis is the azimuth. That means that the sensor is basically flying in this direction. There are very specific distortions due to the side looking of synthetic aperture radar, and are mentioned here. Maybe the easier one to understand is the shadow. So what is shadow? So if you assume that this is our object and the sensor it's over here, so what we are acquiring, it's basically in this direction. So our sensors transmit and receive signal back. You can understand that whatever is here, it can be captured because it just the sensor just doesn't reach this, no? So it captures it basically. That's an obstacle. So and this area here will be then in shadow. So we won't have any contribution. This appears often as black or very dark in SAR images. Some other phenomena, they are linked again to the geometrical configuration of the scene, and are called foreshortening, where slopes oriented to the SAR sensor appear compressed, and layover, where we have a superposition of different terrain contribution. We have also an image flipping here where the top of the mountain, in the case of a mountainous region, appears actually before the bottom of the mountain. So this is due again to to the geometrical configuration of our sensors and our the geometrical setting of the scene. What is important here is to understand that there are distortions that are intrinsic to synthetic aperture radar, and these make the image interpretation slightly more difficult. So it's not as straightforward as we have for optical images due to this like signal propagation and different angles.